So just to remind you here, the integral is motivated by this geometry problem where we're trying to find the area below the curve. So we're trying to find this area below the curve. And the way the story starts is we partition the x-axis. So here, the axis is going, the interval is going from A to B. And what we've done is we've partitioned or divided this interval into n equal pieces, n equals subintervals. And so, we start to do some notation. These x sub i's here, the x1, x sub 2, x sub 0, those are like mile markers, like when you're driving on the highway. So here, if we start at A or x sub 0, we will get to x1 after we've driven, 1 unit of delta x. So these aren't mile markers, they're delta x markers. We will see an x sub whatever after each time you travel a length of delta x. So yeah, x sub 2 here means we've traveled 2 units of delta x. These are just like mile markers marking lengths of delta x instead of miles. So the whole idea now for approximating the area is very simple. We're going to fit a rectangle under the curve, and then we're going to simply calculate the area of that rectangle doing height times width. So the only issue is, the width of the rectangle is fixed. We will use the width of our subinterval as the width of our rectangle. The only issue is what should the height of the rectangle be? So now the way the theory works is in your ith subinterval, you can pick any y value. You can pick any y value from the function in that subinterval and use that y value as the height of the rectangle, okay? And so now we have some traditional choices that we like to use that are very uniform and make things, essentially easy to teach, easy to talk about. So one choice is in the ith subinterval is to choose the right endpoint. And so that's what we see here is we're using the right endpoint. So go to the first subinterval, look at the right endpoint and use that y value as the height. Then do height times width. And so here you see height and then multiplied by the width of the subinterval to give us the area of that subrectangle. And we just go in this fashion for all the subintervals. I go to the next subinterval, look at the right endpoint, and use the y value at the right endpoint as the height, and then do height times width. And the right endpoint is a choice. The left endpoint is a choice. So here we've done the same procedure, but for each subinterval, we're picking the height at the left endpoint. So we get the height at the left endpoint, multiply by the width, that gives you the area of the subrectangle, and then add it to the area of the next subrectangle. Remember here that this sum is a cumulative sum. It's a sum where we're building up on what we've calculated before. So I calculate the area of a subrectangle, calculate the area of the next subrectangle, and then add them. And so it's a cumulative sum that's building up. The other choice, we like right endpoint, we like the left endpoint. Another choice could be the midpoint. And, as I said, this is known as quadrature. This is when we're evaluating the integral numerically. And it's not how we're going to do integrals in this class, but it is the most practical way to do integrals in general. It's, there's no reason for us to believe that it's going to be easy to find the antiderivative of every function that we ever run into. And there's actually no reason for us to even believe that every function has an antiderivative. So at the end of the day, this type of method, even though it's rudimentary because of our computer technology, this is a very powerful method for evaluating these types of integrals, just as a practical point of view. We're not going to do anything practical. We'll do mean value theorem and we'll use antiderivatives eventually. So that'll come up on Wednesday. So yeah, at the end of the day, we're approximating the area quite simply with the height, where the height is calculated by using any y value in that interval. That's what f of x sub I star represents, that we're using any y value in the interval, multiplied by the width, gives me the area of the ith subrectangle, and then I want to add them all up for all n rectangles. That gives me an approximation of the area. And as I said, x sub I star is a generic notation that represents any point. X sub I star is any point chosen from the subinterval, with popular choices being listed here, right? So if you want the left endpoint, we use x sub I minus 1. If we want to use the right endpoint, we use x sub I. And if we want to use the midpoint, we use x sub I minus 1 plus x sub I divided by 2. So these are our kind of most common choices here, but in theory, it can be any y value from that subinterval. And so now that's how we approximate the area. Ultimately, what we want to do is to find the exact area. So the problems are related. I take the approximation where I'm only using n rectangles, and then I increase the number of rectangles. I try to approximate this region below the curve with infinitely many rectangles. And of course, this is done with a limit. So we take the limit of the approximation for more and more rectangles. And if the approximation using more and more rectangles starts to converge, starts to approach one finite number, then we say, aha, we found the limit of the region below the curve. And we use this special notation to indicate the exact area of the region below the curve. So I will talk more about this limit today. But first, I want to finish up our discussion of these approximations. So here, the actual procedure is not difficult. The notation is highly irritating. So here's a slide of all notation. And let's just go through this a little bit just to get comfortable with the notation. Remember, x by itself represents a variable. However, x sub I, x with a subscript, represents a constant. And in fact, you can think of the x sub I notation as function notation. Here, x sub I equals 2 times I, so x sub smiley face equals 2 times smiley face. You can think of x sub I as function notation. And so, as I mentioned, we partition the subinterval, and what we're using are subintervals of equal length. So each delta x has a very nice formula. And here, rather than memorize the formula, you should tell yourself the story of the formula. B minus A is exactly the length of our interval, and we're taking the length of our interval and dividing it into exactly n pieces. So delta x equals B minus A over n, that makes sense as a formula if I want to divide this into n equal subintervals. By the way, look at what happens to delta x when n goes to infinity while we're here. Eventually, when we want to find the exact area, we'll send n to infinity. Delta x will go to 0. In theory, we will be fitting the region under the curve with infinitely many rectangles of width 0. Each rectangle would have the width of a point. So each rectangle will actually look like a line, and we'll be able to fit infinitely many exactly under the curve and calculate the exact area, in theory. So delta x is b minus a over n. It's the length of the interval divided into n equal pieces. Then that gives us the formula for x sub I, which is a plus I delta x. Again, you should interpret this notation. Remember, x sub I is a mile marker. It's marking how many lengths of delta x we've traveled, starting from A. So if I want to get to x sub 2, starting from A, I would add on 2 more, steps of length delta x. And in general, if you want to get to the ith mile marker, starting from A, we're going to travel, a distance of delta x I times. Okay, so it helps to kind of understand the story of the formula, that it's not just random. You can kind of actually interpret it. It does kind of make sense. So we introduced some notation, a generic subinterval will be called x sub I minus 1 comma x sub I. This is just so that we can standardize our notation for what's a left endpoint look like, what's a right endpoint look like, and what's the formula for a midpoint. You know, this standardizes it in this book. In this book, the ith subinterval always looks like x sub I minus 1 to x sub I, and your midpoint's always then going to have this formula, x sub I minus 1 plus x sub I divided by 2. We're just averaging the endpoints. The book felt it was necessary to introduce this notation x sub I star. And you know, you should really not worry about it. X sub I star is really just to introduce some flexibility in this formula here. I really just want a formula that is doing height times width. And I don't care where the height is coming from. I don't care if this is the height using the left endpoint, the right endpoint, the midpoint, or any other y value in the subinterval. I just want a notation to indicate I'm using, you know, one of the y values from that ith subinterval. So f of x sub I star basically just says we're using some y value from the ith subinterval as our height for our rectangle. And as I said, if you choose left, right, or midpoint, you can replace x sub I star with either x sub I minus 1, x sub I, or the average of x sub I minus 1 and x sub I. And we'll talk about this limit in great detail today. So we'll do a problem like that very soon. So I also want to mention here in this section of calculus, where we're doing these area problems, there are two types of problems that we are typically faced with. And herein lies, you know, this is a potential point of confusion, and this is where some students can have issues. So to approximate the area, in this case, in the approximation of the area problem, n is typically a fixed positive constant. Typically n is given to us and n will be a fixed constant, like 5 or 7 or 100. However, if we are doing the exact area problem, in this case, n is treated as a variable. N is treated as the letter n. And what we do to that letter n for the exact area problem is we send n to infinity. Okay, so this part where we take the limit as n goes to infinity, that'll be the very last step of our procedure to find the exact area. I'll show you. But these are, you know, the difference between the approximation problem and the exact area problem is really significant. And this is where typically students have trouble. In the approximate the area problem, n will be a fixed constant. However, in the finding the exact area problem, n will not be a constant. N will just be the letter n. Okay, and so that's why sometimes when people are trying to do the exact problem, they're trying to figure out what n is, and that's the issue. N isn't anything. N is just the letter n for the exact area problem. So here, let me do this example. This is the example we ended with last time. And so now it's very, very important that I'm aware ahead of time what kind of problem I'm doing here. So here, specifically, we want to approximate the area. So in this case, I'm expecting that n is some kind of constant. And so here you can see they've told us n will be 5. N is the number of subintervals. So here we want to approximate the area using 5 subintervals of equal width, so n equals 5. And the other piece of information we're expecting is which endpoint to use. So here we're told to use the right endpoint to approximate the height of each sub-rectangle. So now the procedure starts. It's very mechanical, you know. I start by identifying what's the function and what's the interval. So here, f of x is given to us to be x squared, and the interval AB is 0 to 5, and n equals 5. So with those 3 pieces of information, you know, I'm ready. I can start by calculating delta x. Delta x is the length of the interval that we're going to divide into 5 equal pieces. So 5 minus 0 is the length of the interval divided by 5. I get delta x is 1. And now once I find delta x, I can find x sub I. X sub I is a plus I delta x. In this particular case, A is 0. A doesn't always have to be 0. Just in this case, A is 0. And as we saw, delta x is 1. So when I do A plus I delta x, I get 0 plus I times 1. I get that x sub I just equals I. X sub I equals I, where I is going from 1 to 5. That's the number of partitions. So that's where I'm getting the 5 from. I going from 1 to 5. And so at this point, what we've discovered, are the mile markers for the partition. It's very important to understand what we've discovered. Using this information that x sub I equals I can figure out that x sub 0 equals 0. Well, that one's easy, but now I can figure out all the other ones. I know x sub 1 will be 1. And I know for this problem, it's not difficult to figure out what the mile markers are. If I want to divide an interval of length 5 into 5 pieces, obviously that's not hard. But this is about the procedure in general. And this procedure will always work. So here, once I know my partition, to me, as far as the approximating the integral problem goes, this is it. We're essentially done. Once I've identified the partition, then the rest of it is kind of plug and chug and bring it home. So let me show you what I mean. See, now what I want to do is go to each subinterval, and according to the instructions here, I want to use right endpoints for the height. So what does that mean? I'm going to, for example, go to the first subinterval, look at the right endpoint, and use the y value at that right endpoint. So I'm going to do f of 1 times delta x for the area of my first subrectangle. Then I'm going to go to the second subinterval, choose the right endpoint, use the y value there. So I'm going to do, my height will be f of 2 times delta x, and then I'm going to add that to the previous area, which was f of 1 times delta x. And then, we keep doing this procedure until we're done here, to go through all 5 subintervals. So the third subinterval here, I choose the right endpoint. So then the area of this subrectangle, this third subrectangle, would be f of 3 times delta x. And then I'm going to the fourth subinterval, pick the right endpoint, calculate your height will be f of 4 times delta x is the area of the fourth subrectangle, added to all the areas of the previous rectangles. And then, last but not least, I go here to the fifth subinterval, choose the right endpoint. My height will be f of 5 times delta x. That's the area of the fifth subrectangle. Add all of those areas together. So it's a very simple procedure once you find the partition, the approximation problem, okay? And so here on this slide, I did it in 2 ways. I did it using the formulas, and I also did it just straightforward. So for me personally, I would do the approximation problem straightforward. I'll show you what I mean. So here, in terms of using the formulas, here we know x sub I star, the sample point that we're using from the ith subinterval should be x sub I because we want right endpoints. And if you look at your generic, this is how the generic ith subinterval helps. So my generic ith subinterval looks like this, x sub I minus 1, and then the other endpoint is x sub I. And so if I remember this generic ith subinterval, I can just look at this and I can literally see, oh, the right endpoint is x sub I. And then I solve for x sub I. So now I can replace, the x sub I with I. So here in my approximation for the area, I'm doing height times width, where the height is calculated at the right endpoint, x sub I star equals x sub I. And then x sub I replace with I because we calculated what x sub I is. And now I'm using the function, which is f of x equal to x squared, and I'm applying the function here. So f of I now is going to equal sigma I squared, I going from 1 to 5. And now we just have to find the sum. And you can do this explicitly. You can just calculate the sum. Remember this, if you expand this, this would be 1 squared plus 2 squared plus 3 squared plus 4 squared, and then stop at plus 5 squared. Or in this case, we actually have a shortcut formula for this. So for this problem, I just used we have a formula. We're given this formula from Appendix B. It's the sum of the squares of the first n integers. Here we can use that formula. But actually, as I said, for me, this is how I would do that problem. I wouldn't do any of that sigma notation stuff. I would, once I find the subinterval, so once I get the subinterval, not even the graph. Folks, I don't even need the graph here. I just need the subinterval. Once I get the subinterval, I can look at each subinterval and identify, for example, here, the right endpoint. These are all the right endpoints of each subinterval. And then now I can use that to, do the height at that point times the width. Here the width is 1, so I didn't write it down. But that's how I'm just now formulating these terms. I'm just taking the height at the right endpoint here of the second subinterval and just plugging it into the function. Taking x equal to 2, that right, and plugging it into the function times delta x. So for the approximate the area problem, I don't mess around with the notation so much. Once I find the ith subinterval, I then know how to find the height. Once I find the partition, excuse me. So now that I know the partition, I can look at each one and literally pick out the right endpoint and make my height times width. So I wouldn't necessarily here do too much. For me personally, each person needs to figure out what works best for them and do the technique that they're most comfortable with. So this next problem, I basically did it without using too many formulas, even though I did write down the formulas because I want you to see it both ways. What does it look like if we did with the formula? What does it look like if we just cranked it out? So here it's the same problem. And when I say same problem, I want you to really be aware, this is an approximate the area problem. I'm expecting n to be some kind of constant. And here we're given n is to be 5 subintervals of equal width. So n is 5. And then I'm looking for which sample point are we going to use? In this case, they tell us to use midpoints. No problem. I start the same way as I did the other problem. Identify the function, identify the interval here, a to b is 0 to 5, and n is 5. Start by calculating delta x. Delta x is the length of the interval that we're dividing into 5 equal pieces, so delta x is 1. Using delta x, I can find x sub I. As you remember, x sub I equals I, where I goes from 1 to 5. And so now, see, to me, this is the whole key now. I have now found the partition. Be careful. The x sub I, these are the actual mile markers. These aren't the midpoints. But once I know the actual mile markers, once I know, x sub 0 is easy. So now I know where x sub 1 is. I know where x sub 2 is. I know where x sub 3 is. I know all these mile markers. Then I can simply average them. To find the midpoint, I'm now just averaging 0 and 1. So I'm just averaging these two. To find this midpoint of 3/2 here, I'm just averaging the endpoints of this subinterval. So the average of 1 and 2, so 1 plus 2 is 3 divided by 2 gives me 3/2, so on and so forth. Here, this last one, this last midpoint here, again, once I find the partition, I can simply just eyeball it. I can literally just look at it and calculate the midpoint. So now I know everything. I know I'm going to use the y value at these midpoints for my height. So for my first subrectangle, I'm going to do f of 1/2 times delta x for my first subrectangle. For my second subinterval, I'm going to do f of 3/2 times delta x. Then I'm going to do f of 5/2 times delta x, f of 7/2 times delta x, and then finally f of 9/2 times delta x. I'm not going to use all that sigma notation mumbo jumbo, here for the approximate the area problem. I don't need to. It's more machinery than necessary. But anyway, I did list all the notation because I want you to see what it looks like. So suppose we did want to calculate. So remember, the sample point that we're using from the ith interval is the midpoint, which is x the notation for the midpoint is x sub I bar. And the formula, though, this is the important part, is we're just averaging the endpoints. The formula for the midpoint is just x sub I minus 1 plus x sub I over 2. And that's exactly what we've done here. That's how I found all of these points. But if you want to see it generically, we can do the math here. Remember, if x sub I equals I can just replace this I with an I minus 1. That'll give me the formula for x sub I minus 1. So here, x sub I minus 1 is just I minus 1. Remember here, x sub smiley face is a smiley face. And obviously, x sub I is just I. And now we can do the arithmetic in the numerator. I plus I is 2I. And we got the minus 1 over 2. And so this would be the generic formula for the midpoint. What does that mean? If I take 1, plug it in here, you get 2 minus 1 over 2, you get 1/2. This is the formula for each of these midpoints. For example, if I plug in 2, 2 times 2 is 4 minus 1 is 3/2. That gives me the second midpoint from the second subinterval. If you plug in 5, 5 times 2 is 10, 10 minus 1 is 9, you get 9/2. That's the midpoint of the fifth subinterval if you plug in 5. And as I said, I'm now using just the y value at these midpoints times the delta x. I just wanted to show the notation here. You know, here we're still doing what you should see is height times the width. It's just the height as at the midpoint. Who cares? And then I actually plugged it in if you want to plug everything in. But as I said, I personally don't care about this stuff. For me, for doing this approximation area problem, none of this is actually necessary. All we would need, all I personally would write down is this stuff. I would skip all of this. I wouldn't do any of this. I would just do this. I would go from once we find the midpoints here, once I know these, I can directly go to the sum where I'm using, the y value at the midpoint times the delta x. Remember here, delta x is 1, so there's no delta x written down. Maybe I should have. But here, these are all height times width. And this, to me, for the approximation problem, this is how I would personally do this. There's not really any need to get into too much notation for this approximation problem. For the exact area problem, the notation is required, and I'll show you how we do that in 1 second. So yeah, here's what the midpoint looks like if you just want to look at the picture. And again, remember, you don't need the graph. All we need is the partition. We need the partition so we can figure out which points to use, for our height. The y values here at these points are going to be our height. And then just do the math, just grind it out. There's no reason to do anything fancy. And here, just for the heck of it, I also included what it would look like if we used left endpoints. So this you should, think about. So here from the first subinterval, you see here's the left endpoint. Here's the left endpoint for the second subinterval, third subinterval, fourth subinterval, fifth subinterval. And that's exactly what you see in the sum up here. All these terms correspond exactly to, those endpoints. So I'll let you take a look at that and work through the left endpoint approximation. So that ends our discussion of the approximation of the area. And the whole point we went into approximating the area is so that we can find the exact area. So here now is the limit definition of the integral to calculate the exact area under the curve. So eventually we will replace this limit definition process with antiderivatives, okay? So right now, we don't know that there's a connection between the integral and the antiderivatives, but we will find out in section 4.3 on Wednesday that there is a connection and that antiderivatives will be another way to do these integrals instead of the limit definition. Here, I just had all the formulas and notation. Again, I think the best way to learn formula and notation is just through repetition. The more you can practice and use it, the easier it gets. So I'll let you review this and just think about the story of the formula, not just what the formula is. And again, here, I wanted to remind you of the two types of problems, because it's here where the big issues happen. And especially the thing I want to emphasize is to find the exact area, n will be kept as a variable or a parameter, might be a more appropriate word than the word variable, but whatever. N is kept as the letter n. As opposed to if we're approximating the area, n will be a fixed constant. Like in the previous example, n was given to us as 5. So here is now the official definition of the definite integral. Just like we had the limit definition of the derivative, this is the limit definition of the definite integral. So given a function f of x, and interval a to b, and some partition, we can define the definite integral of the function f of x over the interval a to b. And here, this interval doesn't matter if this is closed or open, or half closed, half open. The definition of the integral doesn't change. And the definition is, so we use this antiderivative symbol. At the bottom, we write a, and at the top, we write b to reflect the interval over which we're integrating, and f of x dx. And it's equal to this limit. So very carefully look at this limit. Remember here, I'm doing height times width. That gives me the sub area, the area of the ith subrectangle. Then I'm adding all n of them. So that gives me an approximate area. And then finally, I'm using infinitely many rectangles of width 0 to pack in the region under the curve perfectly. And if this limit exists, then we've found the exact area. So if the limit does exist, the integral, the definite integral a to b f of x dx, then we say the function is integrable. We can integrate the function. It's integrable. We are able to integrate it. Just like when the limit definition of the derivative of the function existed, we called it differentiable. Here, when the limit definition of the integral, definite integral of the function exists, we say the function is integrable. So of course, now here's a very important result that tells us that if a function is continuous, or if it has only finitely many jump or removable discontinuities, then the function is integrable. Which means what? If this function here, f of x, is continuous, or has only finitely many jump or removable discontinuities, then this limit will always exist. And that's a great result. That's a great result for our scientific computing. We know that if we use this Riemann sum as an approximation, and if the function is continuous, then that sum will converge, and the larger n we use, the better approximation we get. So that's why this is a big result from the scientific computing point of view. From using the mean value theorem point of view, this says that eventually this will say we can do the integral in a very easy way that doesn't involve the limit. We'll see that on Wednesday. So I wanted to make one final comment here about the actual interpretation of the integral. A lot of folks, including me, will say, oh, the integral represents the area. That's not entirely true. The integral only represents the area under the curve if the function is non-negative. If the function is greater than or equal to 0 for x between a and b, then it's true the definite integral will calculate the area of the region below the function, above the x-axis, and between x equal to a and x equal to b. However, if the function is not non-negative, then in general, the definite integral will represent the net area, which is what? It's the area bounded by the function and the x-axis above the x-axis minus the area of the region bounded by the function and the x-axis below the x-axis. Okay, so let me show you a picture. It's a lot easier if you see a picture. So here's a picture. And so you should look at the graph right. So I just made up a function. I just drew a function. And the region, the area of this region bounded by the function and the x-axis that's above the x-axis, I'm calling that area A1. That's the area, so it's a positive number. So A1 is some number that's greater than 0. And now this other region, so here, for this region here, that's below the x-axis. So this is the region bounded by the function and the x-axis, and it's below the x-axis. Here I'm calling the area A sub 2, the area. So that's again a positive number, okay? So then if you did an integral from A to B, that would represent the net area, which in this case would look like A1 minus A2. The area of the region above the x-axis, you know, and the function above the x-axis and below the function, minus the area of the region below the x-axis and above the function. And this is what we mean by net area. You know, for example, if A2 was 0, if this part wasn't even here, then if this part wasn't even here, then the integral would just be A1, and then yeah, your integral would be the area, you know, your integral from A to C. So yeah, it isn't the area in general, it's the net area in general. And so based on this picture that I just drew by hand, it looks like the region below the x-axis looks like that area is larger. So here, the integral will integrate to a negative number, A1 minus A2, whatever that is, you know. And just to bring the point home, if I integrated from A to C, so if I integrated starting from here and ending here, A to C, the integral would be the area. It would equal A1. If I integrated from C to B, so if I did the integral starting at C, ending at B, the integral would not equal A2. It would be A2 with a minus sign in front of it. You know, just like the derivative is a kind of a vector, the integral is sort of like a vector. Not only is it calculating the area, but it's putting a sign on there to kind of give us the orientation. Here it's below the x-axis, so this thing integrates to a negative A2, where A2 is the area. So that's what we mean by net area, and be careful to say that the integral of a function is always the area. That's not exactly true. The integral of the absolute value is always going to be the area. You know, think about what happens if we take an absolute value here. This will flip up, and then you take the integral, then yes, you can say that's the area, you know, and it'll be a positive number. So here's the anatomy of an integral. I just want to name the parts of an integral. It's important that we know this. So the actual integral symbol is a big letter S. So, you know, think about our sigma notation. We had a big letter sigma for the, because it started with the letter S for the word sum. And so here we're just actually flat out using a letter S for the word sum. And here, you know, we might have f of x sub I times delta x. This Riemann sum is basically a discrete version of the integral. These are basically the same thing. One's a continuous version and one's a discrete version. And I want you to think about those words. We talk about continuous versus discrete. You know, and so here, these are both integrals. One's a discrete integral, one's a continuous integral. This number at the bottom here is called a lower bound of integration. And the number at the top here is called the upper bound of integration. And they're not just numbers floating in limbo, these are actually values of x. So sometimes people might write x equals here and an x equals at the lower bound and upper bound, but it's not necessary because the dx tells us that the variable is x. Although some folks will write down the x because they want to be explicit, or that's just how they feel like doing it, and there's nothing wrong with that. The actual function we're integrating, that's called the integrand. And that's the function we're actually integrating. And this part right here, the dx, that's known as a measure. And here, what are we measuring? We're measuring the length of the domain. Here, dx and delta x is kind of similar. We're measuring the length of the domain. And in a definite integral, the actual variable of the of the integral. So here, this x would be called the, this x here would be called the variable of integration. That's also known as a dummy variable because it doesn't matter. The actual variable doesn't matter. It's a lot like the index in a summation. The index actually disappears. So let's draw the picture of this integral. So here, suppose the function's positive, right? So then the picture of this integral would look something like this. There's my axis. Let me draw just some random positive function. And then here's A. There's A. There's B. And so let me label this picture. So this is the picture of this integral. Okay, it's important to be able to kind of think about the integral as a picture and then go from the picture to the integral also. And here, the y-axis, the axis here would be y, and this axis would be x. So I want you to compare this integral. I wrote the same integral. It's a to b, but now f of t dt. So what's the difference? Let me draw the picture of this integral. So here's my axis. Let me draw the function. It's the same function. Here's a. Here's b. This is y. The only difference is this is now t instead of x. This function here is y equals f of t instead of y equal to f of x, but it doesn't matter. I mean, it's still the same input-output relationship. Here, this is y equal to f of x. It doesn't matter because at the end of the day, both integrals are calculating the same thing, right? At the end of the day, both integrals are trying to calculate the area under the curve and above the axis, and they're both the same. So here in both cases, whether I do integral a to b f of x dx or integral a to b f of t dt, they're both going to equal a constant. And that's why we call this a dummy variable, because it doesn't really matter. It's just a placeholder. We'll talk about this a lot more later. Okay, I'll come back to this in a big way some more, but it's important that you start to realize in a definite integral, this is not an antiderivative, this is a definite integral with numbers up here. The entire integral is going to evaluate to a constant. So whether it's dx, dt, ds, d theta, it doesn't matter if it's a definite integral. And I'll come back to that point. So let me very quickly end here with an example. And so the first thing I want you to be extremely aware of is we're finding the exact area. So what does that mean? N will not be given. And so here you notice they've told us to use left endpoints. Great, no problem. They've told us to use what's called, so I've introduced some new notation, new terminology, a regular partition. That's just another way of saying use a partition with subintervals of equal width. What they have not told us is how many rectangles to use, and they don't need to. Because this is an exact area problem, the number of rectangles we will use will be n, where we send n to infinity. Okay, so look, this starts the same way as the approximation problem. I identify the function and the interval, but here I remember to treat n as a variable. Okay, so now find delta x in the usual way. I take the length of the interval, 5 minus 0, divide by n, which is now just the letter n. Once I find delta x, I can find x sub I is a plus I delta x. A is 0 in this case. Delta x is 5 over n. So multiplying 5 over n and I get the formula for x sub I. It's 5i over n, where I goes between 1 and n. This is the generic formula. If you now let n equal 5, you will get back exactly the same formula we got on the previous set of slides when we were trying to approximate the area with 5 subintervals. This is the same formula, just in a generic form. Like I said, if you plug in n equal to 5, it'll look exactly like the formula from the approximation problem. And now we were told to use left endpoints. So I need x sub I star to be x sub I minus 1. And remember here, x sub smiley face is 5 times smiley face over n. So x sub I minus 1 would just be 5 times I minus 1 over n. So now I'm ready to construct my integral. Here's my integral. Here's the definition, the limit definition. Now what I'm going to do, I'm going to replace x sub I star with x sub I minus 1, which happens to equal 5 times I minus 1 over n. And then I replace delta x. Remember, we calculated delta x here as being 5 over n. So there's my delta x. Now use the function. Now I use the fact that f of x equals x squared, and I apply the function here to this term right here. F of all this junk just looks like 5 times I minus 1 over n, the whole thing squared, because the function is just the square of the input. If we can get it to this point, to me, this is like the tricky part. Up to here, you're doing, if you get to this point, to me, this is the tricky part. The rest of it is just plug and chug. Now we just need to simplify. So what's the order? I first need to evaluate the sum so that everything is just the letter n, and then I need to take the limit. And to evaluate the sum, I'm going to start with the very inside here and simplify this. And I'm going to start by simplifying this square. So I'm going to go ahead and pull that term out and square it top and bottom. And you get 25, and I FOILed out the I minus 1 squared as I squared minus 2i plus 1 over n squared. And so now I can replace that in the limit definition. So here I'm replacing this now. When I square it, I'm replacing it with, this squared term right here. Now I'm going to do the math. I'm going to multiply this 5 to the 25 and this n to n squared down here. So I get 125 times the I squared minus 2i plus 1 over n cubed. Now, the sigma notation only cares about the index I. If it's not an I, the sigma notation treats it like a constant. So this 125 over n cubed, neither one of those is an I, so I'm going to pull it completely out of the sigma notation. And here's that 125 over n cubed that I pulled out. Now I'm going to focus on just this. I just want to get rid of the sigma. So what we're going to now do is distribute the sum to each term, and then using our formulas for the sigma notation from Appendix B, calculate the sum. So here, I'm going to distribute the sum. So it goes to sigma I squared is the first term. For the second term, it should be sigma of, minus sigma of 2i, but the minus and the 2 I pulled out because they're not the letter I. So the only thing that's left in the sigma notation is this I right here. And then distribute the sigma to the last term, which is the 1. And now I can use the shortcut formulas. I know we're given the formula for sigma I squared is this mess, n times n plus 1, 2n plus 1 over 6. And then I can use Gauss's formula for the sum of just I right here is Gauss's formula. And you remember this last sum, we can actually just calculate the sum. That's just 1 added to itself n times. So that just equals n right here. And if you look at this stage, we've gotten rid of the sigmas. If you look right here, there's no sigmas. So the final step is just to do some algebra and to send n to infinity. So let me do the final step here fairly quickly. I might write a couple minutes. I'm going to multiply this out, but I don't need to multiply the whole thing out. I just need the highest order terms because we're going to do dominance of powers. So I multiply n, and 2n to get 2n cubed here as my highest power for the first fraction. For the second fraction, the 2's cancel. And here, if you distribute this n, you get n squared plus n. And then if you distribute this minus, you get minus n squared, minus n plus n, these n's cancel. So at the end of the day, this is what we have. So I've replaced all of this with this, which is right here, simplified, where I did the minus n and the n canceled. So now to end, I'm going to distribute this 125 over n cubed to both terms and do dominance of powers. So when I do that, 125 times 2n cubed is 250 over n, 250 n cubed. In the denominator, n cubed times 6 is 6n cubed. Here, LOT is just the lower order terms. I don't care about the n squared term, the n term, the constant, because I'm doing dominance of powers. 125 over n cubed times minus n squared is minus 125 n squared over n cubed. Then you send n to infinity, you see get infinity over infinity. We do dominance of powers. Here you notice that the degree in the bottom is bigger, so that just goes to 0. In your notes, you might have an extra plus 0 written here. I don't know where I accidentally had an extra plus 0. And this term, the degree on the top and the degree on the bottom are the same. So it's just a quotient of the, coefficients of the highest degree term. So here we can calculate the exact area as 250 over 6 or 125 over 3 or, 41.6. As I said, this is the extremely long way of doing this. On Wednesday, because of the mean value theorem, we'll have a much easier way of doing this using antiderivatives. But as from a practical point of view, quadrature, calculating the integral this way is more practical in the real world because, it's not necessarily true we can find antiderivatives of any function. So I'm going to stop right here and I'll continue here next time.